Welcome back. We are going to be looking at part 3 for acids and bases today. And today it's all about that base. So first thing we're going to do is we're going to talk about strong versus weak bases. So just like acids, there are strong and there are weak bases. And the first thing we do is we're going to look at the strong bases. And so there are 8 strong bases. Real quick way of remembering this is that, well, the definition of a base, first of all, produces hydroxide ion. So you're going to have a hydroxide ion most likely attached to a strong base. So we look at the periodic table. This is 1A, and then this is 2A here. With 1A, you're going to have the elements lithium through cesium, and then in 2A, you're going to have calcium through barium. And so that's 1, 2, 3, 4, 5, 6, 7, 8. This makes your 8 strong bases. So sodium hydroxide is the most common one, and you probably worked with that before in lab. Calcium hydroxide is another common base. These are both strong bases, and you got to balance the formulas out based off the charge. Sodium hydroxide breaks down to form sodium ions plus hydroxide ions, and calcium hydroxide does the same thing. There's a small difference though. The coefficient there in front of the hydroxide is different. So when you focus on the calcium hydroxide, there are actually 2 moles of hydroxide are produced. So that's an important detail when we look at the strong bases, because remember, strong means dissociates completely. So it's going to completely dissociate, it's going to fully ionize. So you have to pay attention to the stoichiometry of the equation as you break it down. Now, when we work with weak bases, everything else is a weak base. So memorize the 8 strong bases just like you had to memorize the 8 strong acids. That makes things a little bit easier to work with and understanding what you have to do. So for bases, we're going to look at the right side of the screen here. We looked at the functional group, just like the acid had its unique functional group, but base does too. The basic group that's the functional group that is basic is an amine group, and so an amine has a nitrogen at its center, and it has 2 hydrogens attached to it, along with a residual, and that residual can be anything for that matter. So once the R group is what's amine attached to, so it doesn't matter. What matters is the fact that you have the amine group. So we look at this example here. This is ethylamine, and ethylamine is a basic compound because it has this NH2 group. So remember that for a base, it's going to Bronsted-Lowry definition here. It's going to accept a hydrogen ion. So this nitrogen has a lone pair on it, so hydrogen can easily fit in there to form the conjugate acid. So the most common example that we run across with a basic solution are NH3 molecules. So NH3 is ammonia. We know we use ammonia to clean with. And now there's a difference here. You can't just say NH3 forms whatever it forms, because in this case it's not like the acids where you just broke it down to form the equilibrium. Here we have to show water as one of the reactants, because the hydrogen has to come from somewhere. So the hydrogen is going to come from the water molecule. So you're going to form NH4 plus 1 plus OH minus. In this case here, the water acts as your acid, your NH3 is your base, and so the nitrogen is going to come in. It's going to take a hydrogen from the water, and it's going to leave you with hydroxide in the very end, which you see here. So unlike an acid where we had CH3 CO2H, all we did was break it down to CH3 CO2 minus plus H plus. A little difference here because you're not having to show any other species. You could, but it's not necessary like it is for the basic solution. So make sure that you always include water with your basic compounds. Now, so when we worked with a weak acid, we use Ka, but when we work with a base, we use Kb. And so we could write the Kb for this reaction, and the Kb, well, B stands for base to begin with, so Kb is equal to NH4 plus 1 times the hydroxide concentration divided by the NH3. So the reason why we don't include water is because water is a liquid. Don't include liquid and solid in your expressions. That's an important detail to remember. Now, another detail is, and we didn't talk about this in the acid part, but we can relate it back to acid. So when we talk about strength of bases, we oftentimes need to look at the Kb values. Kb values can be found in the appendix of your textbook. You can Google these values. And so the higher the Kb value, so the higher the Kb, the stronger the base will be. All right, so as that Kb value increases in value, the stronger that base will be. So we could say the same thing for the strength of an acid. So the higher the Ka, the stronger the acid is going to be. Not meaning it's a strong acid, just means that it's a stronger weak acid. So it's going to dissociate more into solution. So before we do anything else with that, let's just work a simple problem where we take a 2.65 grams of barium hydroxide, place it into solution, and we determine the pH of that solution. Now, barium hydroxide is one of those strong bases, so first thing we do is write the dissociation of it. And so we form barium ions plus 2 hydroxide ions. Now, you're going to have to figure out the molar mass of barium hydroxide, and the molar mass of barium hydroxide is 171.32 grams per mole. So the next thing we're going to have to do is convert that at moles. So take 2.65 grams, we're going to divide it by the 171.32 grams per mole, and we end up with 0.0155 moles of barium hydroxide. Now, that's how many moles of barium hydroxide we have. So to figure out how many moles of hydroxide we're going to have, you're going to do 2 times the 0.0155. Now, that's going to lead us to where we can figure out the molarity of the barium hydroxide, or not, but of the hydroxide. We don't need a molarity, we just need a molarity of the hydroxides. So we're going to take this, and we're going to divide it by 0.735 liters. That comes from right here. Just convert this into liters. So once we've calculated this, we end up with a molarity of 0.0422 molar. Now we want to figure out the pH of the solution. So we're going to figure out the pOH first because we're dealing with hydroxide. So you're going to take the negative log of 0.0422 molar, and we get 1.375 for the pOH. To figure out the pH, we're going to do 14 subtract the 1.375, and we end up with 12.625 for our answer. And then we should get a basic pH as it is because we're dealing with a basic solution. Okay, so we're going to look at another problem here where we're going to rank the bases in order of increasing strength. Now this goes back to what we talked about earlier with understanding that the larger Kb values result in a stronger base. Now, so we're going to let's look at the compounds we have present. So we have a Kb value here, and then we have a Kb here, here, and then we have hydroxides. There's 4 compounds. So right off the bat, let's just go ahead and get the easiest one taken out. Potassium hydroxide is a strong base. It's going to be stronger. It's going to be the strongest of those 4. Now we're going to look at the Kb values. So what is the next largest Kb? Alright, it is this, it's the methylamine here, which is CH3NH2. So that's next in line. Now, make sure you pay attention to the exponent. Don't look at the numbers in front. Look at the exponent here. 10 to the negative 4 is much bigger than the other 2. Now, what would be next in line? It'll be your C5H5N. Because it's 10 to the negative 9th. And then the last one is going to be your C6H5NH2. And that has a exponent of 10 to the negative 10. You can look at the whole number. Sometimes it's easier to look at the exponents, and in this case that's what we did. So one thing I will make a note here while we're looking at this is that you can look at each of the compounds besides potassium hydroxide. You can see that the methylamine, if we draw the Lewis structure for it, as a nitrogen with 2 hydrogens. There's your mean. For the other one, you have C5H5N. So here's your nitrogen. It's going to have 2 lone pair, or it'll have a lone pair on it. And the same thing for here, for the first one. So all of these have mean groups. So that's why they're basic compounds. Now I want to just talk about something else. Is if you see a compound that looks like this, you probably would make the assumption that the OH breaks down to form hydroxide. This is not a hydroxide. This is an alcohol group. And an alcohol group is not basic nor acidic. Alcohol groups are neutral. So this is a neutral compound. Be very careful in understanding whether you're dealing with a hydroxide or an alcohol. Alcohols are always attached to carbons, and they're not going to be acidic or basic. They're going to be neutral. The only time that you're going to work with hydroxides are the 8 strong bases that we talked about in the first slide. So be very careful in your understanding of this, because that'll make a difference in the future. So looking at a new problem here. So calculate the pH of a 0.5 molar ammonia solution at 298 Kelvin. Kb is given to you at 1.8 times 10 to the negative 5. So to start this problem off, first thing we're going to do is we are going to write the dissociation of NH3. Now remember, for the basic reactions, you have to include water, and this breaks down to form NH4 plus 1 plus hydroxide ions. Now we're going to fill in the ice chart because we're given information. So water is not included because it's a liquid. This is 0.5, these are 0 and 0. So this will be minus X. This will be plus X. And this will be plus X. So the next thing I'm going to do is write the expression for the Kb reaction. So Kb is equal to the concentration of NH4 plus 1 times the concentration of OH minus divided by the concentration of NH3, which is equal to 1.8 times 10 to the negative 5. Now we're going to include the equilibrium portion here into the expression. So you're going to have X times X divided by 0.5 is equal to 1.8 times 10 to the negative 5. Now I'm going to assume the minus X is negligible. We talked about the 5% rule in part 2, so we're going to use that rule here. So we're going to solve for X. So in this case, you're going to take 0.5 times 1.8 times 10 to the 5th. You're going to take the square root of that value, and what we get here is 0.003 for our X. So the 5% rule, we're going to take 5% of 0.5, and that's going to give me 0.025. So we need to look at X here. X is going to be smaller than that, so that means that this X is valid. That means we can use that X. If this was not valid, we'd have to go back. We'd have to go and we'd have to include this minus X and use a quadratic equation. But since it's valid, we just go ahead and calculate pOH. So the X is equal to the concentration of the hydroxide ion, and so we calculate the pOH from that. So we get a negative log of the 0.003. And so taking the negative log of 0.003, we end up with 2.5. Now, the question asks for the pH, so we're going to take the pH is equal to 14 minus the 2.5, which gives me 11.5 for my answer here. So, a couple take backs from this problem is you got to write the equilibrium first, making sure you include water so that way you know where the hydrogen came from. And then you set up the equilibrium expression like always. You then include your equilibrium components from the ice chart, and you can make the assumption, but you got to validate it with the 5% rule, and then you go about calculating the pH from the pOH. So moving on into a new problem here, the pH of a 0.1 molar ethylamine is 11.8. Complete the Kb reaction from ethylamine, and then we're going to calculate the Kb for ethylamine. So first things first here, ethylamine is a basic compound. So we're going to write the equilibrium of it, and this is nothing difficult. So don't make it anymore. Find the amine group because that's where the action is going to happen. So what's going to happen here is you're going to add the hydrogen to the NH2. So you're going to form CH3, CH2, NH3 with a +1 charge because you have an extra hydrogen. And you'll be left with hydroxide remaining from the water. Alright, so that's the Kb reaction. Now, the next thing that says calculate the Kb for ethylene, because they don't give it to you. What they do give to you is they give you the pH of the solution. And we're going to use that to our advantage here in the ice chart. So water doesn't matter. Now the initial concentration of this is 0.1. These two are 0. So this is going to go down. So you got 0.1 minus X. And these will go up. And I'm not going to write anything in for hydroxide because I know the pH is equal to 11.8. I can figure out the pOH of the solution by subtracting that from 14, and what I get from that is 2.2, and so the concentration of hydroxide is equal to 10 to the negative 2.2, and what that gives me is a concentration of 0.00631. That is the equilibrium concentration for hydroxide, so that's what I'm going to include here. And one other thing I want to make a note here is that that's also equal to X because of this part of the ice chart. So once you figure that out, now we know X. So what we're going to do next is we're going to write the expression created for Kb. So Kb reaction is going to be equal to C H3 CH2 NH3 plus 1 times OH minus divided by CH3 CH2 NH2. Alright, so we know what these values are. So we know this 0.00631, and this is going to be squared because they're the same. X times X is X squared divided by 0.1 minus 0.00631. And so going through the math, till you plug it in, you square it, divide by that in parentheses, make sure you use parentheses here. You end up with 4.25 times 10 to the negative 4 for your answer. So this is the value of Kb for that particular compound. So a couple of things here. This is different from the other problem because you're given a pH. In the other problem, you're calculating the pH. Here, you're given a pH and has to calculate Kb. So we're really doing things backwards. But the good thing is that once you understand what your X is, it makes the part figuring out the equilibrium much easier to work with. Now, letter D says calculate the Ka value for ethylamine chloride or ethyl ammonium chloride. That's using the information determined in the above problem. So we know Kb was equal to 4.25. We just calculated that. But how to go from Kb to Ka? Well, that's where you use Kw. So Kw is equal to Ka times Kb. So if we want to figure out Ka, well, we just take Kw and divide it by Kb. Well, what's Kw? We talked about that in the first part. It's 1 times 10 to the negative 14. We're going to take that number. We're going to divide by 4.25 times 10 to the negative 4. And what we end up with is 2.35 times 10 to the minus 11. So this is a basic compound. So yeah, the Ka value should be small in relation to that. So, but that is the last problem that we're going to cover in this part. So for our recap, we talked about what acids and bases are. We talked about strong versus weak and how we deal with strong acids versus weak acids, and now we're dealt with strong acids versus weak bases. So it's just a matter of going through and working these problems and just making sure that you understand the differences between the acids and the bases. So thanks for watching. Next video will be talking about salts.